Hello. In today's class, we're going to talk about pipelining processor. Well then, let's get started. All right, this is the section 1, part 1 of the pipelining processor. In this slide, we're going to talk about pipelining concepts, potential speedups, how to make your processor work with pipelining, and the details issues related to pipelining, which we call hazards. And at the end of the day, we're going to talk about solutions to pipeline hazards. Well, let's first start with the big pictures of pipelining. Well, intuitively, I would assume that you all know about pipelining, but you just didn't have a chance to call it pipeline. Why did I say that? Well, it's kind of natural. Let me give you a quick example. For example, you have assembly line in a factory. In this example, we got SUV assembly lines in a factory. Now let's assume that you got about 5 stations for the assembly line. As soon as you finish the first station, you move it to the second station, you can start the next car right away. This way, rather than having 5 cars, each one got 5 hours rather than use 25 hours, we can use, well, first 5 hours to fill the pipe and plus 1 for each hours. So we got 5 cars, we got about 9 hours. Right? So that's why I say pipeline is natural, and in fact, you do it every day when you order food in the cafeteria or do the buffet. So let's me move on a little bit and do more analysis of the pipeline. All right, in this example, we got laundry. For those of you who may not familiar with laundry, laundry is basically a process to clean your clothes. And in general, you would do washing. After you do the wash, in several countries, we have no sun because it's winter, so we do the dry. So we have washer, dryer. After that, you do folds and stash. Let's assume that each step take about 30 minutes. So I got 4 person, and Brain, Katie, and Dave. They all want to do pipelining. Sorry, they all want to do laundry. All right. So if each person have to do laundry, there are about 4 steps. Each step contain about 30 minutes. So one person would take 2 hours. Now I got 4 person. This is for Anne, for Blaine, for Katie, and for Deb. With 4 persons altogether, I would need 8 hours. Pretty long, right? But you may observe that, wait, by the time that Anne is finished with the washer, why don't we just start next batch of washing clothes for Brain right away? If you do it that way, we can reduce from 8 hours to maybe 4 hours, or 3.5 hours to be exact. This is the pictures, right? And finish. Oh, we got the washing machine free. So we start washing the next one. And by the time that we finish the first batch, the second batch almost finished. This is pipelining, or in a sense, when you got the resource available, just start. So what we have learned from pipelining? Well, one thing that you may have noticed that pipelining doesn't make any particular task finish faster. Like in this case, A or N still take 2 hours. B, Brain, still take 2 hours. So each person still take 2 hours. Right? But if we take a look at the overall, rather than use 8 hours, we can now reduce it to 3.5. So we, in a sense, pipeline help with the throughput. It do nothing with the individual tasks. If we talk about speed up, this then go from about 8 to 3.5, so it's 8 over 3.5. What else we have learned from pipeline? It is that each step depending on the slowest state. For example, let's say that this guy can fold closest maybe in 15 minutes, but still we cannot start folding the next batch right away because we still wait for the previous step. And unbalanced pipeline is actually the things that make the pipeline go slow. So the nice thing to do is that make sure that each step take the similar amount of time. In fact, we have learned about this concept when we do multiple cycle processor. And in case you didn't notice, for pipeline, you would take few hours or few steps to fill the pipeline. And once you fill the pipeline, right after that, you would take approximately 1 cycle to finish each batch. And at the end, you also have to drain the pipeline. So this is the time that when you don't have fully utilization of the pipe at the beginning and at the end. But given that if you have several loads of laundry in this example, well, filling and draining the pipeline, that doesn't matter. It's only few amount of time. All right, let's try to generalize our pipeline a little bit. Let's say I got K loads. So can you do the calculations of how many hours would it take to do the pipeline? Okay, let's try with something simple. You would take at least n cycle to fill the pipeline. For our laundry, you would take about 4 cycles to fill the pipeline. So our pipeline, our execution time is like this. It's 4 cycles to fill the pipeline. Once you're done with the 4 cycle, you would take about 1 cycle each to finish each load. If we got K, since the first 4, you already finished the first load, you only have to finish K minus 1 load. And each cycle is actually half an hour. So we can time 0.5. Totally, you would get what? 2 plus K minus 1 times 0.5. Right? This is a generic function of the pipeline. In fact, the number of load would be the CPU instruction count, and the 4 would be the state of pipeline. Anyway, we're going to revisit this equation again when we talk about pipeline performance. This is just give you a head start about what would be the performance of your pipeline. All right, let's talk about potential speedup. So we will use multiple cycle processor as a baseline, assuming that we have k number of instructions. Right? If the multiple cycle has CPI equal to 5, so k times 5 times cycle time would be the CPU time of the multiple cycle processor. For the pipeline, you would need to first fill the pipeline. That would equal to the number of pipeline state, assuming that we have 5 state of pipeline. After you fill the pipeline, there would be k minus 1 instruction to finish. Each instruction would use 1 cycle. So this would be the CPU time of the pipelining processor. I'm asking about speed up, so you just divide the CPU time of multiple cycle processor by the CPU time of the pipeline processor. you would cancel out the cycle time. Eventually you would get 5k over 4 plus k. If you have a lot of instruction, we can take limit k to infinity. That would give you about 5. So maximum speed up or ideal speed up would be 5 and no more. All right. Now for our processor, to have a pipeline, it just fit nicely with our 5 states. So this is 5 states of the load instruction. You got fetch, decode, execute, mem access, and write back. It just happened that this is also 5 states of our pipeline because it's kind of fits nicely. When you want to draw a pipeline, there is some kind of notation. When you want to say read, we would have darker shade on the right hand side. And when you want to say write, you will have darker shade on the left hand side. On the top, this is standard processor, multiple cycle processor, and this is the pipeline processor. So these pictures, I just want to compare to you the single cycle processor, multiple cycle processor, and the pipeline processor. You would see that this is one big cycle, CPI equal 1, but TC would be pretty long. Then we decide that we want CPI to vary between 4 and 3, 4 and 5 and make TC pretty short. And for the pipeline, we eventually decide to push CPI to be 1 with short cycle time. Now a little bit of exercise again. Suppose that we have 100 instructions. If our single processor got 45 nanoseconds per cycles and our multiple cycle processor got 10 nanoseconds per cycle with the average CPI of 4.6, and the ideal pipeline machine has 10 nanoseconds per cycle with 4 states. Alright, what would be the CPU time of each one and the potential speed up? Let's do the math for the single cycle processor. CPU time would be 100 times 1 times 45, right? And for our multiple cycle processor, our CPU time would be 100 times 4.6 times 10. And for our pipeline processor, we would get CPU times equal 100 times 1 times 10. Well, if you want it to be exact, we have to add 4 cycles for the pipeline filling. Alright, let me quickly rewrite this again. It would be 4 plus 100 minus 1 times 1 altogether multiplied by 10. Alright, speed up. Then let's try speed up for the pipeline processor, comparing to the single cycle processor as a baseline. So you would get 100 times 1 times 45 divided by 4 plus 99 times 10. Alright, so you would get 45,000 divided by 130, 1030. So you see that it's obviously faster. Well, given the performance, there is no reason not to use pipeline, right? Because we got all the resource to just modify the control a little bit. So you can start the instruction right away when you got a free resource available. But wait, pipelining is also not perfect. We know that the world is not perfect. Pipeline is also not perfect. Pipeline in several cases can also get you into trouble. That kind of trouble, we call it pipeline hazards. And we have three kinds of hazards. We call it structural hazard, data hazard, and control hazards. From the name, structural hazard means you have limited resource. You got instruction that you want to start, but wait, we don't have resource to start. So we have to wait again. Data hazards mean your data is required right now, but it's not ready. Like it will be done in the future. So we call that data hazard, or sometimes people call it dependency hazard. And control hazard, meaning you got free resource, but you don't know what to do. Let me clarify that a little bit. Start with structural hazard. Structural hazard means you may need two resources at the same time. For example, if the laundry machine and if the washer machine and the dryer machine happen to be the same machine, meaning you cannot start washing the next batch because that same machine is still used by the first batch for drying. So this is structural. You ready to start the new one, but wait, we don't have the resource that we want to use. Or another example, let's say the folder, this guy is now busy doing something else, so you cannot fold. Alright, this is structural hazard. Again, it's resource that you want, it's not available. The next idea, we call it data hazard. Let's say you want to use something that would be ready in future. Like, for example, you want to fold a uniform with shirts and pants. To do that, you have to make sure that you got the shirt and pants at the same time. But wait, what if shirt is right here, pant is right here? Now you want to fold the shirt, but my pant is not ready yet. It would be ready in the next 30 minutes, so you cannot fold them. Or another example, you got one socks or pair in a dryer, another one in a washer. Once you're done with the dryer, you cannot fold your socks because another one is still in the washer or in the dryer. And for control, resource is a variable, but you don't know what instruction or what batch to start. It's like, oh, I have done. What next? And nobody can answer that. Well, that's comparable to the branch or control. Let me give you a real world example. Let's say you wash football uniforms. The football uniform may require proper level of detergents, but you would know after you finish with the washer or dryer. And you decide, okay, is it clean enough to fold? If not, you have to wash it again. So you have to wait and maybe wash it again. That means you cannot start the next batch right away because you don't know yet whether I can start the new one or I have to redo the same uniform again. Now we have learned about hazards. So what do we have to do? We have to solve them. And to solve hazards in general, you can just wait. Like for the resource, you don't have the resource that you want? Well, wait until the resource is available. Same thing for data. Data hazard, you want to use the data, but the data is not ready yet. You wait for the data. And for control, you don't know what to start. Okay, fine, just wait until you know what else, what next. But we don't like waiting, because waiting means you waste your time doing nothing. That's bad for the performance. So we would try to solve hazards without waiting. And in practical, the pipeline control must detect the hazards and have to take actions to resolve hazards. ใช่แล้วพออัดเสียงต่อนะ
อัดเสียงอะไรอ่ะ
อัดเสียงอันนี้ต่อเนี่ย
เสียงอะไรอ่ะ
เนี่ยวิดีโอเนี่ย Alright, now let's move on and see how would you solve structural hazards without waiting. Since structural hazard cause from limited resource, like in our case, the washing machine and dryer machine happen to be the same machine. So the easiest, or you can guess, solution is buy another machine, right? If washing machine and dryer machine happen to be the same machine, and you want to do two things at the same time, so buy another one. So in a sense, structural hazard can be solved by design or by money. If you put in more money, you can easily solve structural hazards. Right? Let's see structural hazard in a processor. Now we got a processor and we want to solve structural hazards. Where do we have structural hazard in the processor? For example, our memory, data memory and program memory happen to be the same memory. Then we may have structural hazards. How to solve it? If somehow you can make it two different copies, it's like you got one page of paper and you want two persons to read from it at the same time. Well, let's make a copy. One person reads from one, another one reads from the copy. Right? So in our case, we can use two separate cache, one for data memory, another one for program memory. This way, you can read them both at the same time. Again, make more instant available. Well, you may see from this picture that, wait, we might have issue with register since it's the same register. Well, maybe not, because this one you write to it, this one you read from it, and we have designed our register in a way that you can read and write from them at the same time. So this might not be an issue. Let's try another one. What would happen if you mix 3-cycle instruction, like in this case, 4-cycle instructions, the add instruction, and the load instruction, which may require 5 cycles? Here's an issue. When you have 5 cycle coming and you have 4-cycle instruction after, since the add instruction is R-type, it doesn't have to do anything with the memory. So the register write back would move back 1 cycle. Here, we would then have an issue that 2 instructions want to write to the register at the same time. So we now obviously have structural hazard. How would you solve it? Well, first solution, you stall. Another one, you have to redesign it in a way that you don't have to stall. So let's see how would you redesign it. Well, this one is stall, right? But when we stall, you see that we got a wait cycle, and you have to wait all the way, or else you introduce another hazard. We don't like it, because we don't like waiting, we don't like wasted cycle in the processor. Then some people propose that what if we add a dummy state to the instruction with full cycle to the R type. Like this one, we add a dummy which basically do nothing. But with this, we have just solved structural hazard because now we push the requirement for register write back one cycle. Again, this is DC side trade-off. You would have to make the instruction one cycle slower. But overall, it might be better because now we don't have structural hazard. How about data hazard? Well, the obvious one is when you have to do read after write. Like for example, the instruction before would write to register R2, but the next instruction, the one after, say we want R2 for the add, you would need R2 at the fourth cycle, but you would not get R2 until the end of the fifth cycle. So how would you do that? How would we resolve this? Well, obviously you can wait. Add 3 stall cycles. But do you really want to do that? 3 cycles? Maybe not. So another idea is maybe we can forward it a little bit. Well, if you take a look at it, like for this example, the first instruction produce R5. The instruction after want to use R5. Rather than wait until you got R5 right back, we actually got R5 right here. You already got the solution. What you have to do is that you just have to create a special circuit to forward it. It's like I ask you to do some calculation for me. But wait, rather than wait until you finish, I say, I know you're done with the calculation, you just didn't write it back to the paper yet. Why don't you shout it, say it out loud so that I can use it right away? This solution, we call it bypass or forward. Or in some cases, like this one, we have add instruction after the load instruction. Can you really do the forwarding? Well, maybe not. Why? Because the data that you want is here after the end of fourth cycle. But the add, you would need it at the beginning of the fourth cycle. And since we don't have time machine like Doraemon's or the Back to the Future movie, so sorry. So how would you solve this kind of data hazard then? Maybe you have to wait. Or another idea is you ask software to do something. Like we know that you would need 5. Oh, okay. In this example, you would need R2 here, right? But rather than wait, maybe we say we move something up a little bit. That way, we can avoid the R2. We call this kind of solution delay load. Sorry, delay load, meaning you try to move some instruction that don't have to use this register in between. So you indirectly postpone it for one cycle. Like in this example, if you have load R2 and you want to use R2 right after you load, we don't have R2 available. So what if the compiler inserts some instructions that has nothing to do with R2 in the middle? Then we just solve data hazard. Well, in reality, you would want to insert something useful. But if you have no instruction at all, NOP, we short for no operation. That's not a bad idea, given that you can solve it in compiler. How about control hazard? Well, control hazard basically coming from the branch instruction. Well, you want to figure out whether you have to branch or not. That would usually take at least 3 cycles. But until you know the result, that you have to branch. Let's say you have to branch here. It may be too late. So sometimes we just guess, like in this case, if we guess that it's not branch, so we start this 2. And if it have to branch, you just load the branch after that and you just ignore the write back. That way, this instruction seems like it never happened, but you wait maybe 2 cycles. So we can wait. If not, we guess. Statistics say if you guess taken or not taken, you would got a chance to be correct like 50%. But nowadays we got more advanced branch prediction like branch history, which take one history. Like if the previous loop you do the branch, maybe you would do the branch again. This one, it's 90% correct. And if you take a look at branch prediction in Intel processor, Intel claimed that Intel got more than 99% correctness from the branch prediction. But anyway, I will not get into the details of that. But in the past, several people got Ph.D. or Master from branch prediction. So let's try this. What if we ask the compiler for help, and for the hardware, we modify the semantics of our branch a little bit. We call it delay branch. In a sense, the instruction after the branch has nothing to do with branch. So if without the delay branch, this one, you do the branch, but wait, we have to decide right away whether we want to do the branch or not. And since we know that the instruction like number 1 has nothing to do with branch, why not just move it down after the branch? So you would get the one on the right hand side, right? The delay slot means the instruction after the branch has nothing to do with the branch. So branch would decide to go with 3 or 9, not 1. But with this, you always have to ask compiler or software programmer developers for help that, okay, I got free slot, what do you want to do? But on the bright side, you waste nothing, right? So we need support from hardware. Anyway, this is the diagram of the branch delay slot. You would see that we decide one cycle after, and the instruction that come right after the branch has nothing to do with the branch. Okay, that's for the lectures of today. Let's move on a little bit to the exercise to make sure that you understand the concept today. All right, I got maybe tricky equations. You know that when we mix instruction with different CPIs together, we may have structural hazard. My question is then, what if I try to mix store, branch, and jump with the R type, which use only 4 cycles, and this one use 3, or this one use 4, 3, or even with the load instruction. Why don't we have structural hazard at all? Okay, on the left hand side, we have structural hazard because we have load and add. It's read. This one want to read R2 after write. All right. How about the right hand side? Well, I got branch. Why don't I have structural hazard at all? Wanna guess? Well, it's simply because the missing state is at the back at the end. So if the missing state is at the end, why bother? Because I don't have resource conflict at all. So that's why we don't have structural hazard in this case. You would only have structural hazard when the state in the middle is missing, right? If not, we don't have it. Okay, let's try this one a little bit. I say I got add instruction, load instruction, add instructions, store instruction, and add instructions. Together, 5 instructions. Can you identify whether we have some kind of hazard in this? Well, you might want to draw it a little bit. Okay, I draw quick pictures here. This is for the add. This is for the load. This is for the add. This is for store. And last one for the add. Okay. Do we have hazards here? Well, this one write to R10. Alright. This one read from R12, write to R3. This one use R3. This one use R10. This one write to R10. So we got, oops, sorry. We write to R10 here. And we have to read from R10 here. So for R10, we don't have structural hazard. Oh, sorry, data hazard. This one write to R12. Alright, 12. Okay, maybe I use another color. 12 here. Do we need 12 somewhere? Yes. Where is it? We need it here. Alright. This one write to R3. Do we have R3? Here. When do we need it? Here. Alright. Maybe you can do some forwarding to add this, but anyway, I will stop here and leave it to you. Well, I hope you enjoyed the class today. Thank you.